everyone. My name is Mario Lanza. I am an associate professor at the King Abdullah University of Science and Technology. And for me, it's a very great pleasure to chair this nanoscientific symposium, which is organized by Park Systems and Nanoscientific. Today, I am very happy to have this interview with Professor Sean O'Shea, who is one of the inventors of the Conductive Atomic Force Microscope back in the 90s. Professor O'Shea is working right now in Singapore at the A-STAR Institute. And so I think it will be a very great pleasure to know more about this invention. So good morning, Professor O'Shea.
Yeah, thank you, Mario. Thank you. Good morning. Yeah.
So I guess everything is going well there related to COVID-19. Everybody is fine and safe.
Yeah, well, we started working again in the labs. We shut down for a small while, but then we're back and working again. Singapore's been quite good at shutting and controlling everything down. So slowly getting back to speed, but okay, yeah.
Fantastic. Safety is the first. So I think the first obligatory question that me and my students and all the attendants of this symposium may have is if you could briefly describe how it happened, how you and your colleagues came up with the measurement of electrical current at the nanoscale using an atomic force microscope.
Oh yes, thanks, Mario. What was happening was I was working in Cambridge at the time after I did my PhD in Sydney, Australia. So I was working in Cambridge developing AFM there because the AFM was developed in around 85, 86 by Christoph Gerber and Gerd Binning. And so Mark Wellen was my boss there. And so we were developing AFM, a small team developing AFM. And at the same time, one of the postdocs joined from Oxford University, Martin Murrell, who'd been looking at oxides. So he was very interested in looking at how these electrical oxides break down. And it's got quite a good history because the STM itself, one of the reasons they developed STM was to look at thin oxides. So, but in those days, the gate oxides were very thick. They were like over 10 nanometers thick, so you couldn't use STM. So we said, why don't we try and use AFM on these and make them conducting, try and measure the conducting. So what we did with a team of us, myself and Martin Murrell, and a guy called Tim Wong, who developed all the electronics, and we had this very good software sort of digital controller, which was probably the first digital controller ever made for SPM. And so what we did, we got silicon tips and we got some samples from IMEC. Mark Hayes gave us some samples there. So they were state-of-the-art oxides for then. They were 12 nanometers thick. At that time, they were state-of-the-art. And so we used oxide tips, silicon tips. Sorry, not oxide tips, but at the end, we know now there's silicon dioxide at the end. We're highly doped silicon tips, and we just came down to the surfaces, put a voltage on, and measured the current because we had all the STM things in the lab. So we know how to measure small currents. So it's just a question of putting the voltage on, measuring the current. And the only trick we really did was, as you know, for oxides, we have to limit the current flow. Otherwise, as we found out quite early, everything just went boom, including the tip. so again, yes, exactly. So with this digital controller, we could just say, hey, when the current reaches a certain value, just turn it off, turn everything off. So we had a current limiting method directly with software control. So with that, we were able to measure like the IVs and things on the VLSI oxides. Well, 12 nanometer thick VLSI oxides. So that was the first data. So it wasn't so hard to implement. But as it turns out, interpreting it is more difficult than just doing the measurement. Yeah. So one of the reasons we were doing that was there was a debate at the time whether the breakdown voltages being measured like in a capacitor type structure, were actually indicative of the material itself, or were there like localized defects over the capacitor area, which like weak spots that were leading to a lower breakdown field than if you just measured on the oxide itself. So that was sort of our motivation, the question. And we've found very high breakdown voltages in our first measurements using this. We were very excited. Oh, yes, the local fields with AFM conduction tip can be much higher. But it turns out, of course, it was all to do with the tip. So what we were doing, we were working in air, and what we were doing, putting the voltages on, was just growing the oxide or whatever, something underneath the tip. So we needed much higher voltages to break down not just the oxide, but also whatever was growing under the tip. So that was a bit of a red herring. And when we did the job properly a bit later on with metal tips and things like that, we found, and diamond tips, we found that the actual field to break down the oxide was exactly the same or thereabouts as what they were measuring, on the standard MOS type capacitor structures. So,
oh, wow.
So the problem was working in air. So, as you know, you start to grow things under the tip. So we did the usual things. Now we sort of did a few tricks. The easier one was trying to pull the electrons from the substrate. That seemed to stop things growing so much under the tip. So that was, what we found. And then the other thing is to work in vacuum. So we built a vacuum system, and Mark Lance and myself did a fair bit of work there trying to understand the actual conduction AFM and how it relates to the contact area. And there we worked on like slightly more exotic material like niobium diselenide, nice and flat, so that we didn't do so much the breakdown of the oxides, but we're trying to understand how the relationship between the forces and the current flow. And they seem to match all the theories quite well, with the exception that there's still an issue with actual knowing the contact area as an absolute value. You can always see the relative changes, okay, but the absolute values remain very, very difficult, in my opinion, to nail down, for these sort of things. And just to finish that little story there, like this growth of the oxide underneath, we were very irritated with it, because it was mucking up our experiments. And so, how do we get rid of this? And it turns out at the same time there's a group in the US using this to actually do lithography. So they're actually using the phenomena to actually write it down. So we missed out on a good paper there. We thought it was this very annoying thing. It turns out it's actually quite useful to actually do lithography. So it was fun days, trying to figure out what was going on.
Well, that is very interesting, because it looks like it was a little bit unpredictable what could happen for the first measurements, right? Because you encounter some experimental non-idealities during the measurement that affected the values that you were targeting until you could successfully get this breakdown field of the silicon oxide. So you mentioned that in your first experiments, you didn't use a metal-coated silicon tip, you just used a highly doped silicon tip?
Yes, that's correct, And then, so later on, we realized that was part of our problem. We could clean them up in UHV conditions, the silicon tips, but we were having real troubles in air, in ambient. So at that time, we started making our own metal wire tips. We would squash the wires, small wires, between two bits of mica to make the flat bit of the cantilever, and then etch the end using standard etchers, wet etchers. So we were mainly using gold, making gold wire levers like that, hand-by-hand levers. And the other sort of really good thing for us was Philip Niedermann at that time in Neuchâtel in Switzerland was developing the heavily doped diamond levers. So he kindly sent us some of the first levers he was making. We started using those, and they turned out to be much better for our purposes than the silicon ones. So that was interesting as well. So So the silicon levers, metal levers, and diamond levers. And to be honest, I still use those. That's the ones I still use in the lab. It still remains one of the main issues, doesn't it? Like this, the problem with the tip is still, to me, this very difficult problem to overcome in conduction AFM. And whenever something new comes along, I always try it, and I always have the same problems, like getting consistency with the tips. Like, I don't know about you guys out there, but, you come down onto a surface and then invariably, like, not all the time, but like invariably something goes wrong. Like there's something with the tip, or you have to try and move the tip on the surface and get it conducting. We always try and test our tips. We always have something conducting, like to try and test it on nearby. Like at the moment in the UHV system, we can clean them up fairly well. We do an ion bombardment, argon ion cleaning of the tips, and then they're usually okay. Usually, not always, usually. And then in ambient, we always have something nearby. Like at the moment we're working, Alec will give a talk later, I believe, on these 2D materials. They're always resting on something, so we put a bit of gold or something nearby and try and come and test the tip. Is the tip okay? And I would say half the time the answer is no. You have to try and clean it up or do something. And so I think it gets back to this question of quantifying what's going on. That's one of the reasons it's so difficult to actually get absolute values, quantitative values. Relative things, okay, but quantitative still difficult to know what's going on. Even in UHV, it's just difficult. And the problem's the tip. What's happening with the tip electrically.
Because even in ultra-high vacuum, you will have an additional factor, which is the contact force, right? Which not only changes the contact area between the tip and the sample, but moreover, you can add some non-negligible pressure into the samples that could induce other effect in some materials, like, for example, flexoelectricity or piezoelectricity in hafnium oxide. So I think there are many variables in this system. And for that reason, I think it is extremely important to provide information statistically. However, I see conductive AFM is a tool, in my opinion, in which we see that many institutes have an AFM, but few institutes have really experts on conductive AFM who publish papers in which all the values are demonstrated statistically. Normally you see these papers with one IV curve, but in order to be able to understand the conduction of one material, we need to provide not one, but maybe 300. So what is your opinion about this? You guys in your lab repeat the experiments many times. I think this is useful for the students here in us.
Oh yes. Alec, he's a postdoc now. My previous student with Professor Pei at SUTD. Yes, you do many IVs. He will tell you many tips and many, we also to try and figure out what's going on. So yes, statistics is very important because it's probably one of the few handles we have on the trying to get reliable data is to do it statistically. It's a bit like measuring adhesion as well. Like you can't just have one number. Like it's a different community who measure adhesion on surfaces and that, but you never just give one number. Never. They do hundreds of adhesion curves, pull-off curves to get the statistical data because that's what you need. And I think we're a bit the same. It's like you have to try different tips, like same tip, and just see if they give consistent data on a particular sample and do many curves. You must. I think otherwise the data is just a bit meaningless because we don't know what's happening with the tip. So 100% agree with you there. It's like it's a difficult problem, but statistics is the way to tackle it, I think, since we don't have a better handle at the moment on the problem. Yeah. So.
We are lucky that the industry of electrical probes for atomic force microscope have been developed in parallel with the development of this technique. And we have seen many new tips that have appeared. There is one that has become quite popular, which is this solid platinum tips that seem to work quite well, even if there is not much flexibility on the number of spring constants. And also, it seems that sharpening this kind of solid platinum tips is a little bit more difficult than standard silicon tips. So I wanted to ask you if you have used these tips. What is your opinion about this kind of tips?
Oh yes, we like them. Yeah, we do like them. We use them. We've found that the platinum ones, well, at least how we use them, like in contact mode, tend to get a little blunt, but you still get data out of there. So we're sort of trying now the platinum iridium ones that they make, and we'll see if they're any harder. Well, they are harder nominally, but we'll see how we go. But yeah, I think they're a good way to go because, one of the good ways to go. They're like, we also like the diamond tips. We do like this, just the contact area will probably be a bit larger than the other style of tips, because they, in contact mode anyway, they will get slightly blunt, but they do appear to give consistent results. You will always have the same problems, like if layers of something get, like say you have one monolayer of something on the end of the tip, then you'll always get funny results. So there'll always be that problem that you have to resolve, whether it's a solid platinum but at least with the solid platinum, when you remove it, and you can just by scanning or something like this, then you can say, okay, we have no other problems with the tip. We know we've got rid of what's on the end, and it's okay. Whereas the semiconductor ones, silicon or metal-coated silicon, is this really true, or can I really believe it? Because it's not a metal now, it's a semiconductor. Because what we found, like those many years ago when we did our work in UHV, myself and Mark Lance, it's like we could only be really confident about the metal contact, the metal-on-metal contacts. We couldn't be as confident about what we were measuring when there were semiconductors in terms of trying to understand the absolute values. But when there are semiconductor tips involved, we always had a little bit of an issue, We're trying to understand what the actual numbers were coming out. Yeah. You can still get relative changes, no problem, but absolute values, again, a bit of an issue. So, sorry, that was a very long answer to yes, we quite like
very good answer.
Quite like the solid metal type of tips. Whether someone can put one on silicon levers and sort of, people, I don't know if they still do it, but in the old days, people were trying to glue or attach like metal, little tiny metal things to silicon cantilevers and things like to get the solid tip, to get the solid metal tip. I think it's by far preferred. Yeah.
I also, I think this has been great because as you cannot, let's say, damage the coating, you just have the whole tip solid. I think at least you avoid one of these ways of degrading the tips. Of course, if you get things attached to the tip, you still see funny data, as you mentioned. I also wanted to ask your opinion about another important development that some companies are starting to introduce, which is the measurement of current in tapping mode. I think a couple of companies are doing this kind of intermittent contact measurement of current, and I think it is. I have seen in my group that it starts to work better for soft materials like polymers, which is something that for flexible electronics and other fields can represent very important advancement. So I wanted to ask if you have experience on this technique, or what is your opinion about this?
I don't have much experience because we usually use contact because we're always doing these breakdown type measurements at the moment. I think it's a great method. I think especially for like seeing, taking images, to see, conductivity changes across the surface. I think, it's very good. because it saves the tip, which is one of the key things you're trying to do with these tips. No, I think it's a very good method for trying to understand the conductivity of a surface. It just depends. It depends what you're trying to do, of course, in all these experiments. So for our ones, we're trying to be a bit like a capacitor type measurement. The MOS. So we like to sit on the surface, contact mode, ramp it up so it looks a bit like a capacitor. This sort of game. But if you're after like these soft materials in that way, it's probably very problematic to do that. This tapping mode approach is probably very good. Probably a really good way, especially if you're trying to see changes across a surface. And then maybe zoom in, don't you? Probably zoom in on specific parts that are of interest. It's a good way to do it. Because there's no way you'd scan in contact mode. You just don't scan. You don't scan in contact mode. You always damage the tip. So we do the same actually. We image in tapping mode, and then we come down on the regions of interest to us.
I see.
So there's no way you're scanning contact mode. So a very good method, I think. Of course. Tune.
So actually, this is just one of the little developments that have experience in conductive AFM science. We have seen many others, like some companies are also offering logarithmic preamplifiers to measure several orders of magnitude of the current from picoamps to milliamps in the best of the cases. So I think there have been, since you and your friends invented this technique, there have been some developments. I wanted to ask you, what is your opinion and your feeling about this? I mean, did you expect so many developments and that this becomes such a consolidated tool in the world of nanoelectronics? And what is your opinion for the next years? Do you think, is there anything that has been covered yet that you may encourage companies to try to improve their service in that specific field?
Well, give us better tips. but that's extremely difficult, of course. That's very... No, I think there'll always be a need, you see. There'll always be a need because the materials are always going to be there. And even new material, like all these 2D materials, who would have thought 10 years ago we're investing so much effort trying to understand the electrical properties of 2D materials. So I think there'll always be a need for the localized conduction measurements. For this conduction AFM, sure. I think all these things that can help, like you say, the tapping mode type of thing is relatively new. That's been great. For me, the problem is always the tip. Always the tip. The other, of course, the other big thing that we haven't talked about is the Kelvin probe type measurements, and there I think there's some more. For companies trying to develop things, I think doing the Kelvin probe in liquid environments, I think is still a challenge because the more recent methods are like based on phase detection or like FM type detection to get the FM, to get the Kelvin probe working correctly, where the slope of the curves are changing most rapidly. So it's quite interesting to me that that Kelvin probe with FM detection, and it's like if you're trying to do that in liquids, that was one of the big issues in liquids as well. How do you get FM detection going in liquids? Like 15 years ago, it was a big issue to get atomic resolution. So it's it's marrying the Kelvin probe problem, FM detection in liquids, with what had to be done to get atomic resolution in liquids. So that's still a nice open problem, I think. Of course, they do Kelvin probe thing in air and things because the quality factors are higher. So the issues when you drop down to liquids, you have all these FM detection issues and problems again, which are solvable. They're solvable, but someone has to do it. So that would be a nice one for working in liquids. Why work in liquids with Kelvin probe? Because I think you'd get a more understandable interfaces compared to working in air. In air, you always have the stuff on the surface, or you have meniscus or something. You might have a better chance to get good absolute values of the work functions and things if you're working in a liquid. So that would be a nice new new advance, I think, if you FM detection for Kelvin probe in liquids. So it sounds specialized, but I think it might be useful, like as a distinct from air, Air, you always have these uncertainties, I think.
Yeah, I think that is a very special application, and actually that is one of the advantages of the conductive FM that allow us to design measurements in a very special way. Every experiment that I read, I see experiments combining external stress with local fields with the tip, and also different techniques. Actually, I have seen some companies that are trying to integrate multiple tips into the AFM, and also recently my group used one setup in which we use a conductive AFM that was inside the chamber of an SEM to do some piezoelectric in nanowires. This whole thing is quite encouraging, but at the same time quite complex. And I think you have been the pioneer on the study of ultra-thin dielectrics, and but you may agree that this can be used in many other fields, right?
Yes, definitely. Yeah, like just measuring, especially if you get that even a two-probe type method going is of course very interesting to all these people trying to measure conductivity and mobility and things on device level, or just the materials for us, really. If you can verify that things are happening, across a small scale, which is where you want to make devices in the first place, measure those things, measurement. So I was going to say 4-probe, but I was thinking, 2 probes probably enough of a challenge to start with. If you could get that going, that would be interesting as well. So that's like microfabrication of specialized tips, I suppose. Specialized, if you had 2 cantilevers and things like this. Yeah, so the microfabrication will, just in a general, it will always be a big part of this story of, tips, cantilevers, 4-probe, 2-probe. The microfabrication will always be there in the AFM story as people try and develop new things. So, if you're a company trying to develop things, there's always that little niche that, if you can come up with different styles or different cantilevers and tips, the all-wire, the all-solid wire levers, that's a small company now that sort of sells these things. And people like me buy them, So, so there's always that little niche for the microfabrication. The higher end bit, like the actual microscopes and all that, as we know, things have become very consolidated in the last few years, with essentially just 2 large companies controlling a lot of the market. So that one might be a bit harder to break, because things like cost and that really don't come into it so much. People are after performance. You can build an AFM in your lab for like $5,000. I mean, but it's not going to do what you want. So people are really after performance. So that market a bit more tricky. So you've got to look for the niche, at least to start, and see where it goes. Is my humble opinion. Yes.
Very useful. Very useful. So I think before concluding, I have to also to ask you one nearly obligatory question, which is we know for all the problems that we have described and all these non-idealities, especially related to the tip and to the atmosphere, sometimes for CAFM researchers and students, doing conductive AFM measurements can be very complex. We are sure that when we get good results, this is normally a very powerful paper because we can see information at the nanoscale, which is something you cannot do with a probe station. But which advice will you give all these researchers who spend hours fighting with the tips, with the scans, with the atmosphere? Which advice will you give all these students?
Oh, well, how do you advise a student? If you want to get into this game, you really got to have the passion. I mean, if you're just doing it to get little letters after your name, PhD, forget it. What are you doing? You have to have a passion for understanding science at the nanoscale. it's not just conduction AFM, it's like all the things at the nanoscale. There's always uncertainties. It's not like, how do I put it? It's not like engineering at a larger scale and find things out rather readily, rather easily. But at this nanoscale level, everything's a challenge. And so you just have to persevere and stay there and try and find where the science is and just hammer away at it. I have endless weeks. I still work in the lab. I have endless weeks in the lab in utter frustration. So trust me, it never ends. It never ends. So, yeah. So hang in there is my advice.
All right. Thank you very much. I think it's very interesting to know that even the leaders in this field have difficulties and that they are patient in order to work in the right direction to solve them. All right, so I think until here, we don't have more time. We have already consumed the 30 minutes that we had. I wanted to thank you very much for your time. It has been really a great pleasure, and I believe it will be very useful for all our attendants for this nanoscientific symposium. So with this, we will just finish. Thank you again. I wish you all the best in your laboratory, and that this COVID-19 ends soon and we can meet again in the conferences and in the labs.
Yeah. Yeah, thank you very much, Mario. Thank you for your time as well. And we'll see how this goes. And I hope all goes well. Yeah, I really hope to visit you guys across there sometime sooner rather than later. Yeah.
All right. Thank you very much.